All right. So again, I'm going to go through some models. I guess you have seen this at some point, but I just want to reinforce or to make a refresher and maybe add some innovation. So obviously what I can bring to the discussion is maybe a little bit more of microeconomic technique. Uh, uh, and then there's a lot of chapters that are more about concepts and ideas and these things. So I'm gonna just do a mental map of these things quite quickly, but I want to insist mostly in the models. So this is chapter I guess 5. I want to check this. Yes, chapter 5, and it's oligopolistic models, oligopolistic models of competition. So you probably, all of you know, an oligopoly is a market in which you have a reduced number of sellers. So in the examples and in the workings of this subject, you have only 2 sellers, right? You have a duopoly that is sharing the market, and you have several treatments of this duopoly depending a little bit on the structure of the industry, of the nature of the industry. So one kind of duopoly is called Bertrand duopoly. Another type is called a Cournot. And the last one is a Stackelberg. Right, and to differentiate, so in Bertrand, you have price competition. In Cournot, you have quantity competition. And in Stackelberg, you have dynamic competition. Right, so all of this should be familiar. So Bertrand, it's when you have a very quick and simultaneous production process. That means that you can increase your production very quickly, almost immediately, and therefore the quantity variable adjusts immediately, and then your strategic variable, your decision variable, is prices. So you have to decide on the optimal price given the actions of the other firm in the market. In a Cournot duopoly, instead, you have a longer production process, so it takes more time to produce. The quantities produced should be determined sometime before production is finished, which means that your strategic variable is going to be quantities, because you're going to be deciding the quantities that you will produce in the future. And Stackelberg is characterized by the fact that production happens in different times for different industries, where typically you have a leader and then you have a follower, right? And these structures can be amended so that you don't have a duopoly, but you have, I don't know, 3, 4, or 5 enterprises. We're going to focus on the duopoly case. And what I want to do is put a little bit of emphasis in the in the games, in the game strategic features of these structures. Okay, so let's start with Bertrand. I imagine you remember, most of you remember how this. Oh, my page is not new. I thought I had a new page. Oops. Bear with me. I'm gonna take a second. I'm gonna take this with me. All right. So Bertrand. So in a Bertrand competition, so your quantities adjust immediately. So what you're gonna get is that you have a price competition, and basically you have a discontinuous profit function in which your profits can be described in this way. So if you have two firms, their profits can be described in two ways. For all of these models, we're going to suppose that first demand. Let me maybe write here the common assumptions that I'm going to make. This is linear demand. So I'm going to suppose that demand is given by something like this, right? Or maybe I'm going to put an uppercase Q, but uppercase Q is the summation of the production of firm 1 and of firm 2. And I'm going to suppose also constant marginal costs. So I'm going to suppose that the marginal cost of any enterprise, it's the same for both, and it's lowercase c. In the subject guide, I use numerical values. I'm going to avoid numerical values so that I can be a little bit more general. Obviously, these principles should be very similar. Things should work out with nonlinear demand, with non-constant marginal costs, but this just adds mathematical difficulty and doesn't give us much more, insight on what the model tells us about how the industry works, right? And if this is the case, we can put that the Bertrand profits are the following. It is the price of the market minus the marginal cost. So this is the profit by unit produced times the quantity produced by the firm. So I'm putting firm 1 here. So I'm gonna do maybe lowercase. So this is clearer, lowercase, and this is going to be the profit. The profit if the price of firm 1 is smaller than the price of firm 2, right? If not, my profits are going to be P1 divided by C times Q1. So how much I win by unit produced multiplied by the number of units that I produce divided by 2 if I share the market, if the prices are equal. So this is a common assumption that I'm going to split the market in 2. It's not really that important, but it's not really that important how it's divided, but the idea is that it's less than if I have the complete control of the market, if I have the whole market. And finally, my profit is going to be 0, and it's going to be 0 if my price is larger than the price of the other firm, right? So this is a very common structure. Competition is in prices, so my strategical variable is price. And this is what is going to be important. And then I can do something like represent this. So typically what we look for in this kind of settings is the best response function, right? The best response function of any firm. And so the best response function. So for firm 1, which should be a response to whatever the other firm is doing, is going to be what is the price that I'm going to set as a function of the price of my competitor. And you know this, you guess this. What I'm going to do is that my best response is to ask for the same price than my competitor minus a tiny fraction of money, an epsilon, because if my price is slightly smaller, then I'm going to capture the whole market. Maybe there is, I can modify this, and I'm going to be a little bit more precise. This is possible when what? When the price is strictly larger than marginal cost, and when price is strictly smaller than monopoly price. Okay, so obviously interrupt me whenever you have a question. Why should this be? First, it should be obvious that my price should never be lower than the marginal cost, because obviously if price is smaller than marginal cost, then I'm making a loss at every unit sold. So I should not do this. And I should not ask for a price larger than the monopoly price, because the monopoly price is obviously the best condition possible. It's when I am in complete control of the market. I am the monopolist. I have no competition, no threat of competition. So in the best circumstances possible, I know that there is a price that is optimal for the monopoly. And this price that is optimal for the monopoly, obviously, it's an upper bound. It's the best I can do, is the highest price that I can take. If I ask for a higher price than that, then the effect is that I'm reducing demand too much compared to the margin that I'm getting by unit sold. Is that clear?
Yes, it's clear, Joaquin.
Okay, great. So what we typically, and so things are going to be symmetrical, obviously. Things are going to be symmetrical for the other guy. So again, he's gonna react in a similar fashion. And I'm supposing that both firms have the same technology. So what I want to represent is my best reaction function. So this is not in the book, but I think it's a nice graph. So I'm gonna put here price of firm 1 and firm 2. So these are the strategic complements. I'm gonna draw the 45 line here, if I can. So 45 degrees line, this is when you have equal price among the two. And then I want to draw the best response function of the firms. So if I draw the best response function of firm 1, what do I know? I know that there is a minimum, right? So I'm never going to ask for a price that is lesser than this. And then after that, my price is going to be a bit smaller. So this is the best reaction function of firm 1. My price is going to be a bit smaller than the price set by the other one. So if I am in the line, the prices are exactly the same. And if I shift a little bit to the left, then I have that P1 is less than P2, right? If I can take it to the extreme, if I take it to this point, obviously P1 is 0 and P2 is not 0. So obviously to this extreme, P1 is smaller than P2, but it's sufficient to be a little bit to the left so that P1 is smaller than P2. And now I know that for each unit, for each value of P2, I want to ask a little bit less. So my best response function moves parallel to the 45-degree line up to this point where I have the monopoly price for firm 1. So I cannot ask more. It's not exactly down there. This is the monopoly price. Yes? So this is the best response. This is the best response of 1. Is it clear?
Yes.
Yeah? Okay. If not, you can always ask me to explain again. And so again, for firm 2, what is going to be the strategy of firm 2? Firm 2 is never going to ask less than C. So this is the minimum. So given that I'm supposing the same marginal cost for both, they're going to intercept at the 45-degree line. I'm going to maybe zoom a little bit. Then the best response of firm 2 is to ask a little bit less, a cent less than my competitor. So I'm going to ask for a little bit less than my competitor. I'm going to be a bit to the, to the right or under the 45-degree line. And then I have again a maximum. It is never convenient to ask for a price that is larger, than the monopoly price. So this is the best response of firm 2. So these are the best responses, and therefore I need to look for a Nash equilibrium. So this is when the best response function of one firm coincide or intercepts with the best response function of the other firm, and then I can start from any point that you want. I'm gonna do a couple of drawings. So suppose that firm 1 begins with this. So I want to know what is the best response of firm 2. The best response of firm 2 is to do this quantity, but if this is the best response of firm 2, then the best response of firm 1 is here. Then if this is what P1 does, then the best response of P2 is here. Then if P2 does this, the best response of P1 is this. And if 1 does this, the best response of 2 is doing this, etc., etc. So what we get is that the dynamics, whatever point you start with, are going to be that you converge to the point in which the marginal cost is equal to the price, right? In the Nash equilibrium, you're gonna get that the optimal strategy for both firms is to set the price equal to marginal cost. If you begin from here, you're gonna have the same. If I'm pricing below the marginal cost, the best response of firm 2 is to price at the marginal cost, and the best response to this for firm 1 is to ask the marginal cost. So we converge also immediately to this Nash equilibrium. Yes?
Yeah, it's all clear so far.
Great. So I think this is the most complicated one, actually. And so there should not be any problem, which implies obviously that, you know, profits are going to be zero because price is equal to marginal cost, which also implies that for demand, you're going to have that P is equal to alpha minus beta. So this is Q. And so we can say that the overall quantity in the market is going to be alpha minus C, because the price is equal to the marginal cost divided by beta, which is the same that you would have if you had perfect competition, right? So if you had an infinite, or at least a very large number of firms. And the other thing that we should remark that is important is that if you have price competition, note that with price competition, which is a Bertrand competition, so the strategic variable is prices. Prices are strategic complements in the sense that they move together. Therefore, if my competitor decreases its prices, I'm going to decrease my prices as well. If he or she increased their prices, I would do the same. but obviously it's never in the best interest, right? It's never a best response to increase prices. But what is important is that prices are moving together, they're moving downward together, so they are called strategic complements. Yeah. Okay, so that's Bertrand. There's really nothing too complicated. I think the graphic is neat. I think it's very pretty. I think it's interesting. So this is something that should be quite easy to solve for all of you. The other one, which you probably are more familiar, which is typical, I'm sure you had examinations around this already, is Cournot. No, so Index 2. So Index 2, and so you have Cournot competition. So this is quantity competition, And here I'm going to take the structure. So you all know this. If I take a representative firm, what is this representative firm going to do? So here things are continuous. We don't have the discontinuity that we have in we don't have the discontinuity that we have in the in the Bertrand duopoly. And what I want to do is maximize. So let me write everything. So I want to maximize the price that I'm going to get multiplied by the quantity I produce minus the marginal cost times the quantity, subject to the fact that price is equal to alpha minus beta, so Q1 plus Q2. I'm going to disaggregate this so I can substitute this in my objective function, which gives me that I have so price times quantity. Let me write it like alpha minus beta Q1 minus beta Q2 multiplied by Q2 minus QC1. So this is revenue. This is total revenue. This is total costs. And if I derive this thing, so I'm going to take the derivative with respect to Q1. What I'm going to get is so the first order condition to get a maximum is going to be alpha minus beta Q, sorry, 2 times beta Q1 minus beta Q2 minus C, and this needs to be equal to 0, or again, I can call this alpha minus 2 beta Q1 minus beta Q2 is equal to C, where this is marginal revenue, and then I get marginal cost, which needs to be equal. I'm putting this detail because we're going to need to remember marginal revenue when we do double marginalization in a few moments, hopefully in a few moments. Just notice that if things are linear, you can write this as no, that's okay. Let's leave it like that. Which means that I can rewrite everything. I can rewrite everything as the following solution, in which Q1 is equal to. So I hope I won't be making any mistakes. This is alpha minus beta Q2 minus C divided by 2 beta. It's all correct, right? I didn't do any mistake.
Yeah, it's correct.
Good.
Joaquin, I think that in the objective function in the second line is the total revenue multiplied by Q1.
Oh, yeah, okay. So this is annotation problem, right?
Yes.
Yeah, okay. Sorry. Good. Okay, so we have this, and this is our best response function. This is our best response function. So this is the best response of one, which is a function of whatever two is doing. And as you can see, if the other firm is increasing its production, I'm going to reduce mine, right? In this case, when we have price competition in a Cournot model, we have that my strategic variable, that is quantities, here is a strategic, or my variables are strategic substitutes and not complement, because they go on opposite directions, right? Why do they go on opposite directions? Let's try to have somewhat of an intuition. If my competitor is going to increase its production, by increasing its production, it's going to be reducing the price in the market because there's more goods in the markets. So what I can do as a best response is to reduce my own production in a way that the impact on prices due to the increment of production of firm two is not too important, right? I want to mitigate, I want to reduce the impact that the increase in production by my competitor has on prices. And how do I do that? By producing less, I will avoid that prices go down by too much. Yeah, so this is the reason why I'm reducing production, which means I'm sacrificing profits in a way, and actually my profits are gonna depend, they're gonna depend negatively on the production of the other guy, obviously. And so if the other guy produces more, I'm gonna sacrifice production, I'm gonna reduce my profits, I'm gonna sacrifice a bit of quantity produced, but what I'm going to win is to avoid a too drastic reduction in prices, which maintains my profits optimized. They're not at least as good as I can do it, given whatever the other guy is doing, right? So we have that in this case, quantities are strategic substitutes, right? And this is related to what I was explaining yesterday, that we need to be very careful when we are distinguishing between substitute goods and strategic substitutes, right? Strategic goods refers to the preferences of the consumer. Strategic substitutes refers to the strategic action that a firm is going to do in response to the actions of the other firm, right? Because things are symmetrical, by symmetry, I know that the best response of firm two is going to be symmetrical. So given that they are solving the same problem, they're going to get, or at the same problem, but only the subindexes change. They're going to get the same solution with the subindexes interchanged. And then we can graph this thing, right? We can graph this thing. So I'm gonna try to do this a little bit carefully. So this is the space. So in the space, I'm always drawing the strategic variables, right? So this is the decision variable of the firm. And so this is something that I see often when I correct micro exams, that there is a confusion on which one is the strategic variable. So I don't know, make a note, repeat it, I don't know, but you need to memorize that Bertrand refers to prices, that prices are the strategic variable, that then you're thinking about very short, almost immediate production times, that Cournot is about quantities, and quantities is about longer production times. So therefore you need to decide on quantities, and the strategic variables are quantities, right? So in the graph, obviously you will need to represent the strategic variables, because what we want to draw is the best response functions of these firms. Okay, let's begin with one. So the best response of firm one, which is this one. What I can do is maybe it is quite visible that the slope of this thing is constant and negative, right? Maybe it's worth separating this in alpha minus c 2 beta minus beta times 2 divided by q2. No, sorry. It's just q2 divided by 2. q2 divided by 2, and I'm going to do the same here, alpha minus c 2 beta minus q2 times divided by 2. Okay, so this tells us q1 divided by 2. So best response function of 1, what happens when q2 is 0? When q2 is 0, this is valued alpha minus c divided by 2 beta. I'm gonna put it a little bit. I'm gonna put it a little bit to the left. I hope I can do this. Yeah, that's fine. Good. And I will have also that if q1, so I'm looking at this function, right? If q1 is worth 0, so I need to think a little bit. If q1 is worth 0, then I will have that q2 is equal to alpha minus c divided by beta. Maybe I should not be lazy. Huh? I should do the computation. So just to be complete, if q1 is equal to 0, this will imply that alpha minus c2 beta is equal to q2. 2. This simplifies. Oh, this simplifies, and so I got the right answer. This is correct, and my slope is minus 2. So I'm gonna move things a bit. Oh, I should have used some color. There we go. And so in terms of the response function, the best response function of firm 1, I'm gonna get something like this. So this is firm 1. This is firm 1. What else? So let's think a bit about this. So this is the best response function. This is internal. Does something happen in the axis? I need a best response, which means that I need a correspondence or an interception for each value of the strategic variable of the other firm. That is, for whatever the other firm is doing, I need to have an appropriate response. So if firm 2 is doing whatever between 0 and alpha minus c beta, if it's doing 0, I'm going to choose this quantity exactly. What happens if the other firm does more than that? What happens if firm 2 does more than alpha minus c divided by beta? What is my best response? What should happen in this sector? I should produce 0, right? If the other guy is flooding the market, right? And if there's really too many goods in the market, my production is just going to drop to 0, right? And so I'm going to be on the vertical axis because Q1 is going to be 0. And then as the price, as the quantity of the other firm, as the quantity of the other firm goes down, what I'm going to do is produce more. So there are strategic substitutes, right? I'm gonna increase my production if the other one. I'm gonna increase my production if the other one is decreased. Yes, things are symmetrical for the other firm. Things are symmetrical for the other firm. So you have alpha minus C2 beta, and then alpha minus C divided by beta. I can draw also a best response function, which is going to be something like that. So this is best response of 1. Then I'm going to do in green the best response of 2, which again should have a response for whatever the other firm is doing. So my line continues here. This is the best response of 2. This is the moment to ask questions if you have any. All right, so we want to know. Yeah.
I'm sorry, could you repeat that last part about being symmetrical? The last green line.
So
it's just what happens to firm 2, right?
So it's just what firm. So the graph is going to be symmetrical. We know that the best responses are symmetrical. So the only thing that you're changing is the subindexes. Whatever was with subindex 1 now is with subindex 2 and vice versa. So in terms of the graphic, what it happens is that this is really, geometrically speaking, this is symmetrical, which means that I can do all the computations, I can be very careful, but the fact is that because I'm only interchanging the subindexes, the only thing that I'm going to do is interchange the axis. So basically axis 1 is going to, or axis Q1 is going to take the role of axis Q2 and vice versa. So I know that the best response of function 2 is going to look very similar to the best response of function 1. So that means it's going to be a straight line. That means that the intercept for its own quantity is going to be the same than here. I know that the intercept in the other quantity is going to be the same than here. And I know that I'm going to have this flat line along the axis if the quantity by Q1 is too large, then firm 2 is going to produce 0. So it's really a geometrical interpretation of symmetry. And then again, this is a general property that you can have for whatever problem that is like this. Now, if you have two agents and if the agents behave in the same way, they have the same problem, the only thing that we are interchanging are the subindexes of the strategic variables. That means that graphically you're just interchanging the axis.
Okay, thank you, Joaquin.
Yeah.
I understand.
Good. So, and then you can just verify that by redrawing everything. You can redraw everything. Trust me, it's correct. So this is a way of winning time. The only thing is that you have to be sure when you read the problem that things are actually symmetrical. If you have one agent that behaves differently from the other, then things become a little bit more complicated. Good. Just we want to verify stability of Nash equilibrium. Well, first we want to see if a Nash equilibrium exists, and if it exists, if it's stable. So again, the same technique can be used. I take whatever starting point I want. Let's say I start with this quantity. So suppose 1 does this. What is the best response of 2? The best response of 2 is to produce this quantity. And if 2 produces this, what is the best response of 1? The best response of 1 is to produce this quantity. And if 1 produces this quantity, the best response of 2 is to produce this quantity. And if 2 produces this quantity, the best response of 1 is to produce this quantity. And then 2, it's here, and etc., etc. So you will have that. I'm gonna put a nice rainbow here, that you will have a convergence. You will have a convergence towards this point. Sorry if it's a bit messy. I'm gonna take another color. I thought rainbows would be nice, but not really. Good. Right, and if you go from the other side, you're going to get exactly the same. So whatever your starting point, you're going to converge to that. This happens because notice that the best response function of 1 has a steeper curve than the best response of 2. If this is not the case, which should never be in a Cournot, right? In this general setting, you always have a Nash equilibrium, but suppose that the slopes are not like this, that the slope of the best response of 1 is flatter and of best response of 2 is steeper. In that case, instead of converging toward that point, we will have a diverging thing, right? This is not the case. It will not be the case in any Cournot problem, and it's not the case because we have seen by the general solution, we see that you have like this, you have like this this half a unit slope all the time. So that's not going to be a problem that emerges. Right. So we need to compute this guy. And to compute this guy, what we need to is to find the best response to the best response. So basically, I need to find the best response. Now, if Q1 is gonna be the best response of Q2, and if Q2 is gonna be the best, so the best response of 1 to Q2 is gonna be the best response of 2 to Q1. Putting things together, I can substitute and say that Q1 in equilibrium is just the best, is just the best response of 1 to what? To the best response of 2 to the best response of 2, which is a function of 1 itself, which means that this is an equation with one unknown. Therefore, we should find a solution, a unique solution, if things are correctly specified. So there's different ways of doing this. We can do substitution. We can do. We can even write it in matrix form if you want. I don't think that's very useful. What I prefer to do is to use the. So there's two possibilities. So these are little techniques that will allow you to take to win some time. I like to start from the first order condition. Let's start from the first order condition. And so for the guys that are taking microeconomics, this is going to be helpful to know these tips. So two tips. First one is, no, so there's a beta that is missing. First one is knowing that results are symmetrical, knowing that results are symmetrical because the agents are solving exactly the same problem, and this works only if the agents solve the same problem. then you're going to get that Q1 is going to be equal to Q2 because they're solving exactly the same thing. No, this is actually on the 45-degree line. We say that things are symmetrical. So if this is the case, everything becomes much easier because I can simply state that alpha minus 2 beta Q1 minus beta Q1. I can just do the substitution, is going to be equal to 0. So Q1 is equal to Q2, which is equal to, let me do a little bit of gymnastics here. So this is alpha minus C 3 beta. So this is one technique. And if things are symmetrical, this is a legal move. There's nothing bad with this, but you need to justify. You need to state explicitly, because the results are symmetrical, because the agents are solving the same problem, we know that the equilibrium is going to be symmetrical. That means that the quantities are going to be the same. Therefore, I can just substitute one of the variables in my problem, and then I get the result very easily. Right? And this is for if you have n firms, this is going to be true for the n firms. The other way of doing that, this is mostly useful if you have many firms, is to compute first the aggregate quantity. And so I can compute the aggregate quantity in the following way. I know that the first order condition of 1 is that alpha minus 2 beta Q1 minus beta Q2 is equal to C. I know that the first order condition of 2 is that alpha minus 2 beta Q2 minus beta Q1 is equal to C. So I can add both. I can add both things, and this is going to give me 2 alpha minus 2 beta Q uppercase, because I'm adding Q1 and Q2, minus beta Q, and this is equal to 2C, which tells me that the overall quantity is going to be, so I need to think a little bit about what I'm doing. It's going to be 2 times alpha minus C divided by 3 beta. Right. So so the idea here is that if you have 2 firms, but this works very well if you have a large number of firms, and if you have, even if things are not symmetrical, so if you don't have symmetry, you can always take this way of solving things, of expressing everything in the aggregate quantity. And once you get the aggregate, you can retake any of the first order conditions, and you can write the so the first order condition, I can rewrite the quantity that I'm going to produce as a function of the aggregate, So maybe I need to be a little bit careful, but there's nothing too extraordinary. So this is alpha minus C, and then I get a plus, is it plus? No, this is minus minus beta, the overall quantity. Now let me be a little bit more detailed here, because I think it's important. So the first order condition is alpha minus beta Q1, so this is the one it's interesting to me, minus beta Q, the aggregate, right? Because I have Q1 and Q2 here, so I can add those up. I need to separate these 2Q beta Q1 in 2 parts, so I leave it alone, and then I join the other part. This is equal to C, and then I can see that Q1 is equal to alpha minus C minus beta Q divided by beta, or I can write this as alpha minus C beta minus the overall quantity. And if and here I can make a substitution. Here I can make a substitution, but I have like a generic solution. No, I can apply this for all the firms. So Q1 is going to be alpha minus C divided by beta minus 2 times alpha minus C divided by 3 beta. The common denominator is going to be 3. So this is 3 times alpha minus beta, and this I can write down 3 times alpha minus C minus 2 times alpha minus C. This is alpha minus C divided by 3, which is minus 3 beta, which is indeed the solution, right? So that works too. It's obviously longer, but it's foolproof. You cannot fail if you do this, right? So this technique is really good. You write in a linear form your first order conditions, you add them up, you obtain the aggregate quantity, and then you plug back your aggregate quantity in the first order conditions, and you'll get the solution. You cannot miss if you do this. It's simple. You see there's not many lines, and you don't need to do too complicated substitutions. Computations become relatively easy. Is that fine?
Yes, everything's fine. Okay, thank you.
Okay, so again, this you can win a lot of time if you do this. Obviously, if you get symmetry, use symmetry. There's absolutely nothing illegal about that, and most very famous, very important papers start from a solution of symmetry and demonstrate everything around that. This is true, for example, for bargaining solutions. No, I don't think we're going to see that now, but so the symmetry move, it's always legal, and it makes you win a lot of time. Only you need to state it very, very clearly. So by taking into consideration the assumption of symmetry, we know that results will be symmetrical, and then you can work these things out very easily. Good. Let's take a break, 5 minutes, and we'll come back to see Stackelberg and then differentiation, and then we'll chat about a few ideas that come in the other chapters. Good. Let's do now the last, well, not the last, because there's an additional model, but one of the classical models for duopoly, which is the Stackelberg leadership model. And I suppose most of you remember this, but it's worth doing again, in which you have a sequential set of decisions, in which you will have, again, I'm going to set the problem like this. So the inverse demand function is alpha minus beta, and Q is the overall demand. So Q is going to be, I'm going to put different subindexes. This is whatever the leader is producing, and this is whatever the follower is producing, in which I'm going to have that the follower needs to maximize its profit, so it's going to be price. Times whatever he's producing minus, oh, sorry, the notation is going to be confusing. So whatever he produces minus the cost of producing it, but with the issue, or the difference, that given that the follower is happening in period 2, the quantity produced by the leader is already given. So this is a given. I'm going to work on basis on that. And from here, I should obtain a best response function from the follower, which is going to be a best response function of the follower as a function of whatever the leader was doing. And once I have done that, once I have solved the second period, then I can solve the problem of the leader, because for the problem of the leader, he wants to maximize, or she wants to maximize profits. She's going to decide on whatever quantity she wants to produce, but also she anticipates the decision of the follower, which is a function of what the leader is doing. So she knows, the leader knows how the follower is going to react, and therefore when I'm going to make my decision of how much units I'm going to produce, I have to take into account that my decision is going to influence on the follower. Yes, and so this happens in the first period. Right, so we solve things by backward induction. We first solve the last stage of the game, and then from the last stage of the game, we use that best response function and we plug it in the problem of the leader in the first period. And so things should be relatively easy to do. Right, so let's do that. Let's solve this problem. So in period 2, what the follower is doing is going to maximize, choosing the quantity and the quantity that he wants to produce, and given that whatever the leader has produced is fixed, right? It's a given for him. So I'm gonna have something like this, right? So the first order condition to get a maximum here is going to be alpha minus beta QL, so whatever the leader is doing, minus 2 beta QF, and this needs to be equal to the marginal costs, because it's marginal revenue on the left-hand side and marginal cost on the right-hand side, which I can solve such as the production of the follower is going to be given by alpha minus C minus beta QL star. So the optimal decision of the leader, whatever it is, the optimal decision of the leader divided by 2 beta, right? So this is the best response. This is the best response of the follower. And then I can plug that problem back in the problem of the leader, sorry. So I'm going back to period 1. Maybe maybe we can write it also in this form. So alpha minus C2 beta. I'm not really sure if this is going to make things simpler or not. Let's see what happens. No, again, strategic substitutes in this case, which means that if the leader produces more, the follower is going to produce less. So we have strategic substitutes, and then we can solve then for the leader. So always, the trick here is always to know how to write the appropriate optimization function, right? We need to be very careful in what goes where and when, and if you do that right, then you should not have any problem. So here we have the leader, and the leader is going to maximize, is going to try to find the quantity of production that is going to maximize his profits. She knows that she has an influence on the price, but also she knows that the follower has an influence on the price, and that the follower is going to do what is going to produce alpha minus C to beta minus QL star divided by 2. This is multiplied by the quantity that the leader is going to do minus QL, right? So we need just to do the appropriate substitution, which is plugging back the best response of the follower into the problem of the leader. And so I don't need a star here because now sorry, my connection is a little bit unstable. I don't need a star there because now it's a decision variable for the leader. Before doing many derivations, you see that this animal is a little bit ugly. We can do some simplifications, right? So there is some things that we can do, and I'm going to write. And so this is important for Stackelberg, also as a way of winning time and as a way of making calculations easier. A good idea is always to find a common denominator for whatever you have as the inverse demand function, as the price. So what you need to look is for the common denominator, and I see that my common denominator is going to be 2. So 2 is my common denominator, and I can put inside of this. So I will have 2 alphas, then I will have 2 beta QL, then I will have minus beta times A minus C divided by beta. So the betas are going to be canceling each other out. So this is alpha minus C. And then I will have, so the common denominator is 2 here. The beta comes there. Careful with the sign, careful with the sign. So always do this very calmly. So this is beta, this is plus beta QL, QL minus CQL, right? So always be very, very careful at this stage. Be very prudent. And then there's some simplifications again. So I have 2 alpha minus alpha, I get an alpha. Then I get minus 2 beta QL plus beta QL. So this is minus beta QL. And then I get a plus C divided by 2 QL. I'm going to write a little bit better. So this is beta QL plus C divided by 2 QL minus CQL. Okay, we got it. So this is sufficiently simplified, and so this is the hard part. Once you have that, it's very easy to find the first order conditions, which are going to be, so I'm deriving by QL, which gives me alpha plus C divided by 2. This doesn't change. Then I get minus beta, beta QL, so this is going to be to the power 2. When I derive the 2, is going to go down, and it's going to be canceled with the other 2. So this is QL is equal to C. Is that correct? So at the end, the leader is going to be producing. So here there's a little bit of, there's a few tricks that you can do. For example, if you have a common denominator that is 2, you're gonna get C minus 2C. So this is gonna be alpha minus C divided by 2, everything divided by beta, and we got the solution of the leader, which means that for the follower, we had it, where is it? We had it here. So this is the follower. Can I put them on the same Yeah, should be able to. So this is gonna be alpha minus C divided by 2 beta minus half of alpha minus C divided by 2 beta. So this is a quarter. The common denominator should be 4 beta, which means that I'm going to multiply 2 times alpha minus C minus alpha minus C. This is alpha minus C. And when you have these things, you always have like this, you always get like these simple solutions. So you shouldn't get any exponents, you shouldn't get weird stuff. You usually, what you will get is a fraction. You usually will get like a fraction, right? Some constant number of the difference between the intercept in the demand function, the marginal cost, and then divided by the slope of the demand function. So you're always going to get a result that looks something like this, and this guy is going to vary according to who you are looking at, which is very neat because it allows you to do comparisons with the other structures, with the other market structures, right? For example, here we can see that where is it? We can see that here it was a third. Here it was, oh, sorry. Here it was a third of this difference between the intercept of the demand, the marginal cost divided by beta. Here it would be half, which means that the leader is producing more, and here it's a quarter, which means that the follower is producing less, right? So this makes comparisons very easy among the firms, right? Did we compute this for Cournot? For Bertrand? For Bertrand, we did not compute this, but basically you would get like the full production. So production is divided by 2, so you will get, you're producing always more in Bertrand, in Cournot a little bit less. And if we add up these things, you get, so if we add them, so here the total added was 2/3, and in the other one should be 3/8, and 3/8 is more than, I don't know if 3/8 is more than 2. No, it's obviously less than, oh. So yeah, in this one you're producing less than in the Cournot monopoly, the duopoly. Yes, correct. So it's always important to compare here profits. You're always going to get this comparison of profits. And so for the follower, what are the profits? Is the difference. Oh, first I need to compute the price. So price is going to be alpha minus beta, alpha minus C2 beta plus alpha minus C for beta, which is alpha minus beta. So this is 2, this is 3 alpha minus C divided by 4 beta, which is alpha minus 3/4 of alpha minus C, which is 1/4 of alpha minus plus 3/4 of C. So this should be also obvious. So if the intercept is larger, the price is going to be higher because you have more demand. And if the cost is larger, you also going to have a higher price because it's more expensive to produce. So that should make sense. And then the profits are, the profit for the follower are 1/4 of alpha plus 3/4 of C. So this is the price minus the cost. Oh, I actually don't need those parentheses. Minus the cost times whatever I'm producing, and I'm producing alpha minus C to beta, which gives me, so let's be careful here. So I get 1/4 alpha minus 1/4 C multiplied by alpha minus C to beta, which gives me alpha minus C 8 beta. So you see, it's again, it's gonna be all proportional. It's all proportional to alpha minus C over beta. So the model is, I guess, sufficiently general, at least to describe a linear demand function and a marginal cost and a constant marginal cost. So you always get like these fixed proportions, right? You always get a proportion of this alpha minus C divided by beta. So this is an easy way to verify that your results are correct. And obviously for the leader, profits should be larger, and I can check that profits are larger. So this is price, this is cost, and I'm producing alpha minus C. How much was it for the leader? For the leader is 2 beta. Oh, sorry, I did a mistake here. This is 4, right? This the production of the production of the follower is 4. So this is 16. Okay, this is 16, and then here it's okay. This is 2 beta, so I already know the result. This is gonna be 8 beta in terms of profit. So the leader obviously gets more money than the follower. And this is a general result. Yes? Is that fine?
Yes, it is.
Good. So as you see, this is simple. It's easy to do. Maybe some practice is involved, but some tricks, some tips that I can give you is that you're usually gonna get something proportional to this alpha minus C over beta, and so this allows you to verify the results quite easily. You should always get that the leader gets more profits than the follower, and comparisons between different monopoly structures, between different duopoly structures should be quite easy to do. The next one in the subject guide, it's somewhat a different problem, because we are looking at enterprises that are competitors, but not direct competitors. So we are thinking about products that are differentiated. So maybe take another color. Models of differentiation. So these two companies are not competing for exactly the same market, or you could say that they are not selling the same product. You have two different kinds of products, right? However, you have a degree of substitution between the two, right? So you could think about this as the function of demand for product Q1 is going to be, you might have an intercept as usual. So I'm taking the example of the book. You have an intercept. You have what is usual, which is a negative impact of your own price. So this is law of demand, and the law of demand tells you that in most cases, except for some very specific cases like giffen goods and things like this, you usually have a negative relation between quantity and price, but also that you have the incidence of the price of another good in the market. This means that you have some degree of substitution between the goods for the consumer, from the point of view of the consumer. And that means that if the price of the other good increases, this is good for you because your consumers are willing to buy more of your own goods. And it's bad news if the price of your competitor goes down, because then your consumer is going to substitute away from your product towards the other company, right? And this is what this positive sign means. This positive sign, by definition, the fact that if you derive the quantity of one good by, if you take the cross derivative, and this is positive, then you talk about substitute goods. Sorry, my connection is a little bit unstable, and therefore the actions of the other guy have an incidence on my own decisions. So I'm going to take the example from the subject guide just to have the reasoning behind this. So suppose as is done in the book, that marginal cost for any company is 0. So we're going to simplify a little bit the problem. And so the profits of firm 1 are the following. I'm going to take into consideration that my demand is affected by my own price and by the price set by the other companies. So there is substitution. Maybe something that I should tell before is notice the coefficients here. If products were perfect substitutes, I can perfectly exchange one for the other, the coefficient should be the same. If there is different coefficients, for example, here, the coefficient of 4/3 is larger than the coefficient of 2/3. This means that there are substitutes, but not perfect substitutes, and that therefore an increase of 1 unit in the price of my competitor is not going to have the same impact than a decrease of 1 unit in the price on my own price, right? So this gives you obviously a magnitude on how easy it is to substitute things. If obviously the coefficient in front of P2 is 0, then I don't need to worry too much about this. It's not my competitor actually, so I don't worry too much about him. But the larger is the coefficient in front of P2, the more I should be concerned about whatever my competitor is doing, right? And this is obviously going to have a repercussion. And I'm gonna multiply this quantity by price. So I'm multiplying this by my own price. So this is for firm 1. And I'm supposing that marginal cost is 0. So I'm going to get 0 in my marginal cost. If I derive my profits, so I'm setting prices. I'm setting prices here. I'm deriving by my own price. So this is going to be 40/3 minus 8/3 of P1, because again, P1 is going to be multiplied by itself. So it gives me a square, and when I derive this, the 2 is going to be in front of everything. And then this is going to be treated as a constant, so this doesn't change, and this is equal to 0. So you can see from the first order condition that I can, solve or figure out the relation between my own price and the price of the other guy. Which I will write it as P1 is equal to, so this 3 they can cancel out. I have 40 divided by 8. 40 divided by 8 is 5. And then I get 2 divided by 8. This is a fourth. This is 1/4 of P2. And this is a best response function, right? This is a best response function. This is the best response of one to the pricing policies of the other guy, right? And so maybe notice that this quarter comes from where? This quarter comes from 2 being divided by 8, and this 2 comes from here. So obviously, the larger the coefficient, the larger this coefficient, the more important is the substitution effect, the more I need to react to whatever the other agent is doing. And if I have a large coefficient there, if there's high substitutability, then I'm going to be very sensitive to changes to what the other agent is doing, right? Here, then, prices are in this case strategic complements, strategic substitutes. Prices are strategic substitutes, which means that I'm gonna decrease my price if the other guy increases its own price. Right, and then again, if I have like something that is symmetrical, if I have things that are symmetrical, suppose that the demand for good 2 is symmetrical. That means, and it's reasonable to suppose that things are symmetrical if goods are substitutes. Then I will get that the best response function is also symmetrical, and then I can do a graph, right? So this is P2, this is P1, and if I do P2, it's gonna be 5 and a slope of 1/4, so this is 20. And given that things are symmetrical, so if the price of goods, so this is the best response. This is the best response of, let me draw it in another color. Whoops. This is 20, so this is the best response of 2. So I need a response for whatever the other guy is doing. If the other guy is setting a price larger than that, I'm gonna set my price to 0, and probably I'm just not going to enter in the market. And for firm 1, so things are symmetrical. So I have a 5 here, I have a 20 here. I should have something like this, and this is the best response of 2. Is this Nash equilibrium stable? I should always check for stability. And if I check for stability, I start at any point for P1. So if I take this point for P1, I take this point for P1, and the best response of 2 is to do this, and the best response of 1 is to do this. And then I verify that indeed I'm going to have convergence. I'm going to have convergence towards, it's not very clear with that color, I'm going to have convergence towards this point. Towards this point. Right, and the same is going to happen here. Well, it's numerically, there's nothing too sophisticated in computing the values, so I'm going to ignore it, even though, so I know that things are symmetrical. I know that things are symmetrical. So P1 is equal to P2 because they are solving the same thing, which means that this fraction is always annoying. I'm going to write it like 20 P1 is equal to, oh, sorry. 4 P1 is equal to 20 minus P2, which means that 5 P1, oh, I'm going to write everything as P1 because they are symmetrical, they are the same. So 5P1 is equal to 20, which implies that P1 is equal to P2, which is equal to 4. And then we have it. And you should be a little neater than me, but I just wanted to do this. Right, and once I have the prices, I can compute the quantities, I can compute profits, etc., etc. Yes. Easy. Any questions? Okay, I'm going to suppose then that everything is fine and in order. Okay, so that's like the most micro chapter, I guess, at least from what I have seen up to this point. And the following chapters are a little bit more about, you know, theory, ideas. There's not much mathematization. There's almost no mathematization. So at this point, I want you to make a choice. That is, would you have me try to explain some concept and ideas that come in the following chapters, or given that there's almost no math in it, you prefer to read it on your own? I'm gonna pause the recording for this part.